Welcome back everybody to another video lecture from Miss Semino. The title of this video is Equilibrium Video Number 4. However, I think that this video I'm going to be using for my AP Chemistry students as kind of an introduction to thermodynamics. So for you guys that have had me before, you're like, this PowerPoint font looks really familiar. It is. This actually comes from your honors textbook, but it'll, like I said, be a good introduction for thermodynamics. Our primary objective for this chapter is to describe the role of entropy in chemical reactions. Now, pay attention to this word entropy. It is different from another word that we've talked about before, enthalpy, and I'm not the most awesome writer there. Okay, so remember, enthalpy was the change of heat in a reaction. We're going to see that entropy is the rate of disorder within a reaction. So these two things are different. And we're also going to identify two factors that determine the spontaneity of a reaction. And the way that we can determine the spontaneity of a reaction is to calculate Gibbs Free Energy. So I'm just going to go ahead and read through this slide and then we'll talk about it. So free energy and spontaneous reactions. So many chemical and physical processes release energy, and that energy can be used to bring about other changes. The energy in a chemical reaction can be harnessed to do work, such as moving the pistons in your car's engine. So when we talk about free energy, this is the energy that is available to do work, and that does not mean that it can be used efficiently, though. We'll see that some energy might be lost as heat. Okay, so on this slide, we're just going to go ahead and talk about efficiency of things. So your car's engine is only about 30% efficient, and this is used to propel it, to make it move forward. The remaining 70% is lost as friction and waste heat. So we all know that our engines get hot when we are running them, so a lot of that energy produced from the gasoline is actually going out as heat. So it also says here that no process can be made 100% efficient. I think this is kind of an interesting factoid. Living things, they're the most efficient. They're still only about 70% efficient. We can only get energy from a reaction that actually occurs, not just theoretically. So if we look at this reaction here, we've got our carbon dioxide decomposing into carbon and oxygen. It says that this is a balanced equation and is the reverse of combustion. But however, experience tells us that this does not tend to occur, but instead happens in the reverse direction. So we know going in this direction is more likely scenario. So the reaction that we're seeing here, this carbon dioxide decomposing, is not likely to be very spontaneous. So when we're talking about balanced chemical equations, we can divide them into two groups. We can divide them into equations representing reactions that do occur, or equations representing reactions that do not occur, or at least they don't appear very efficiently. So the first of that category are those ones that are spontaneous. And so in a spontaneous reaction, it occurs naturally and favors the formation of the products under specific conditions. They produce substantial amounts of product at equilibrium and release free energy. And then, of course, the other one are the non-spontaneous reactions, and these do not give substantial amounts of product at equilibrium. I really like this example here. So if you're drinking a soda pop, the carbon dioxide comes out on its own, and so we'd say that this is a spontaneous reaction. So that's going to, happen on its own. However, the carbon dioxide going back into the solution happens very little, and so that would be considered a non-spontaneous reaction. So it is important that when we're talking about spontaneous reactions and instantaneous reactions, we don't want to think that spontaneous reactions are going to happen like automatically or like right away. There's lots of spontaneous reactions that totally occur, but they take actually a really long time for them to happen. I like the examples that they're providing here. So sugar and oxygen do produce carbon dioxide and water, but a bowl of sugar appears to be doing nothing. However, it is reacting, but it would take thousands of years for that bowl of sugar to completely react. Another example here is at room temperature. It is very slow. Apply heat and the reaction is very fast. Thus, a change in conditions, temperature, or pressure may determine whether or not the reaction is spontaneous. So we're going to see how temperature and other conditions like pressure can affect if a reaction is spontaneous or not. The other classic one that we talk about is like the rusting of a car. You'll see some rust appear, but it's not like it happens overnight. Okay, finally we're going to get to entropy here, and so we'll often see entropy with the delta S, so remember a change in entropy, S is standing for entropy. Before we were looking at delta H, and that was a change in enthalpy. This has to do with heat, hence the H here. This is for the disorder of a system. So entropy is a measure of the disorder and is measured in units of joules divided by moles times Kelvin, and there's no negative values of entropy. The law of disorder states the natural tendency for a system is to move in the direction of the maximum disorder and not vice versa. I love this example. So your room never cleans itself, does it? So there's a tendency for systems, such as your bedroom or your desk or your backpack, to become more disordered over time. In order to order it, it's going to require some energy to do that. So when we talk about entropy, an increase in entropy favors the spontaneous chemical reaction. A decrease in entropy favors a non-spontaneous reaction. So on this slide, I'm going to go ahead and talk about the pictures, and then we'll go ahead and we'll look at the words here. So if things are getting misordered, or more disordered, I should say, we're having a solid turn into a liquid and then into a gas. So you can see there's a very orderly arrangement, still orderly but less orderly, and then like completely crazy and not ordered. So that's why we have an increasing entropy here. Here again, kind of the same idea. You have a lot of particles together, very structured. Still some structure, no structure happening. Let's see. So here we've got our water, very ordered. And then over here, they're less ordered. There's more pieces here. When I talk to my AP chemistry kids about this, I like to say that there's more possible arrangements because you have more particles on this side. There's more like patterns or more ways that the particles could be arranged. Here, since you have fewer particles, there's fewer ways that they could be arranged. The example I think we'll talk about is, let's say you had 5 knickknacks and you put them on your windowsill. There's only a certain number of ways that you could put them in order, okay? But if you had 7 knickknacks on your windowsill, there's way more different arrangements that you could put them in. So when you have the 7 knickknacks on your window, there's going to be a higher entropy there because there's more ways that you could order those 7 things than the order of the 5 things. And then, of course, down here we're going from not very hot temperature, applying some heat, so we're making it more disordered, and then more different arrangements here because the particles are moving fast. So it says the entropy of a gas is greater than the entropy of a solid or a liquid. Factoid, remember that. Entropy increases when there are more product molecules than reactant molecules. So this is kind of my example of the knickknacks on your window. Entropy is increased when a substance is divided into its parts, so like having more particles there. And entropy increases when room temperature increases, and that's because you're making those particles move faster, potentially. Even if they're still staying in the liquid, they're having more heat and more room and ability to move around. So now we're going to go ahead and talk about enthalpy and entropy. So when we look at reactions and we want to see if these reactions are going to be spontaneous, spontaneous reactions generally do 2 things. The reactions tend to proceed in the direction that decreases the energy of the system. So we've looked at a lot of graphs, and we always say that those ones are spontaneous when the products are at a lower energy level than the reactants are. And that's why often particles will form bonds, so they're at a lower energy. The second thing does deal with the enthalpy. Reactions tend to proceed in the direction that increases the disorder of the system, or that entropy. Going back to that bedroom example, it's more natural for your room to get messy than it is for it to get clean. Go ahead and tell your parents that. So these 2 things, a decrease in enthalpy and an increase in entropy, are called drivers to every equation. If they both agree the reaction should be spontaneous, it will be spontaneous at all temperatures, and you will not be able to stop the reaction without separating the reactants. If they both agree that the reaction should not be spontaneous, it will not work at any temperature, no matter how much you heat it, add pressure, or try anything else. So sometimes both of these things, enthalpy and entropy, are not agreeing with each other. Sometimes you might have an increase in temperature or an increase in enthalpy and an increase in entropy, and that might not give you a spontaneous reaction. So we have something called Gibbs Free Energy, and there's a calculation we can do with this. So the size and direction of enthalpy and entropy change both determine whether a reaction is going to be spontaneous. If the 2 drivers disagree on whether or not it should be spontaneous, a third party, Gibbs Free Energy, is called in to act as the judge about what temperature it will be spontaneous and what that temperature is. But it will work and it will be spontaneous at some temperature. Okay, so here is that third party or Gibbs Free Energy that's going to help us determine if the reaction is going to be spontaneous or not. So if our delta G is negative, the reaction is spontaneous, and if the delta G is positive, the reaction is not spontaneous, and so it's going to require some energy to be added to make it work. Okay, so here's our delta G, here's our delta H, minus T, and that's the temperature is in Kelvin, our delta S. So our change in enthalpy, our change in entropy here. Okay, so as a review, if the enthalpy and entropy do not agree with each other as to what should happen, Gibbs Free Energy says that they are both correct, the reaction will occur. But if the Gibbs Free Energy decide that the conditions of temperature that will happen at. So we'll sometimes talk about how a reaction will be spontaneous at a high temperature, but maybe not at a low temperature. And so we will be going ahead and doing some more calculations in class using Gibbs Free Energy, as well as seeing a table that we can use. Welcome back, everybody, to another video lecture from Miss Semino. This video, I'm calling it equilibrium video number 4, but just so you guys know, this is probably an AP chemistry video.